Okay. So last time we did what's called Ampere's law, right? And Ampere's law says the following. It's a general law equivalent to the Biot-Savart law, but it takes advantage of symmetry. And so Ampere's law said if you take, let's say you have currents, some of them are coming out, some of them may be going in, maybe you got a current out, another one maybe out of the board, and let's say you draw a loop around them, and you integrate counterclockwise on that loop. You do this, G dot ds over the closed loop in this counterclockwise sense, then this integral will equal to mu naught times all the currents that are inside the loop. You add them up. And you add them up such that the ones that are coming out are positive, the ones that are going in are negative. In the worksheet number 10, we have some problems on the Ampere's law, so we will get some emphasis, some practice with those. And then we did the solenoid. You may remember for the solenoid, I'm not going to go over it again, but it says, so let's say you have a solenoid that looks like this. It has a number of loops per unit of length, and it's used to generate a constant magnetic field that's uniform within the solenoid, but zero outside the solenoid. Ideally, the solenoid would be infinitely long, but you know, a regular solenoid would be this long, let's say, in the lab. And so they're not infinite by any means, but they are long enough such that you can use the following result. It says the magnetic field inside the solenoid is mu naught. We know what mu naught is, 4 pi times 10 minus 7, times n. It's the number of loops per unit of length times the current. So n is the number of loops over length per unit of length, right? And what I mean by, let's say the solenoid has length L, and you count the number of loops. Let's say you get 10,000 loops, and let's say it's 10 centimeters. So you get 10,000 loops per 10 centimeters, or 0.1 meters. So that's 100,000 loops per meter. So that's the number of loops. So that was that. So for both of you, in discussion, I discussed the force on a charge, on a moving charge. So I would like to, I guess, discuss it in front of the camera, so we just have it. And then, but we will do maybe a few more details. So the magnetic force, now the electric field exerts, if there is a charge in an electric field, the force on it, it's the electric force, it was the charge times the electric field, right? We all remember this. And if you like, you can put the vector also. Now, how about magnetic fields? What do they do? And what kind of force do they exert? And what's the nature of that force? Well, experiments show the following. Here is the result. Charges in a magnetic field, they experience the following force. F due to a magnetic field of Fb, and it's equal to Q times the velocity of the charge cross-producted with the magnetic field B. That's the magnetic force. See, the electric force is simpler, just the product of Q and E. Magnetic force has this cross product, not this cross product. So it says the following: if the charge is zero, if it's neutral, does it experience a magnetic force? No. If the velocity is zero, if the charge is not moving, does it experience? No. If the magnetic field is zero, obviously, if there is no magnetic field, there is no magnetic force. Also, it depends on their cross product. So if they're, remember the cross product is the magnitude of the first vector, it's the magnitude of this force, which is the Q, V, B, sine theta. If they are parallel to each other, or anti-parallel, meaning they make 180 degrees or 0 degrees with each other, then there is no force. The force is still 0. Okay? So you need, it depends on a few things, right? And also the direction of motion. So let's figure out the direction of the force I have. Let's figure out the direction of the force. Let's say, here's first example, right? So you have to use the right-hand rule. So let's say the velocity is this way, and the magnetic field is this way, right? In what direction would the force be?
Out.
Towards you, yes. So curl your fingers from V to B. So orient your fingers with V. So there are many ways to orient your fingers with V. But to curl them, see, if I orient them this way and curl them, they're not towards V. So I need to orient this way in order to curl them towards V. My thumb would be pointing this way, and that's the direction of the force. So it will be out of the board. Yeah.
Is velocity in the same direction as current?
Yes.
Yeah.
Because current is moving charge. Yeah. So let's say, oh, by the way, I should say this is let's say a positively charged object. Okay? Positively charged object, V cross B will be this way, and so the force is QBB, so that's what we get, all right? So that's the first one. Let's do another one. Where's the other one? Let's say the magnetic field is now coming out of the board. I still have a positive charge, and let's say the velocity is this one. In what direction would the force be in this case?
To the right?
To the right. Okay. Do we say it's to the right?
Yeah.
I think I agree with that, yeah. Because B is this way, V is this way, so curl your fingers from B to B. That gives you the force to the right? That's the force. Okay, sounds good. Let's do another one. Let's say this is a negatively charged object. Here is the velocity. Here is the magnetic field. Zero. So they're parallel. Sine theta is 0. Yes. So the force here is 0. Couple more. Well, let's say a minus charge, right? It's a negative charge. Here is the magnetic field. Magnetic field is in what direction? Into the board, right? And let's say the velocity is this way. Okay. So I heard up.
Down.
Yeah. Up. Up. Okay. Yeah. So let's see why. The velocity is this way, the magnetic field is that way. So curl your fingers from B to B. That gives you down. Down. But the negative charge flips that vector and makes it go up. So the magnetic force is upward. Any questions? Is this clear? Yep.
Mm-hmm.
Was that a hand?
No, it's just in left hand.
Oh, okay. Okay, so that's that one. Let's do one more. Here is one that you have to think a little bit backward. Here it is. Let's say I'm giving you now the force is this way. I'm giving you the magnetic field is this way. And let's say the charge is positive. Right? Just in what direction is the velocity? So, yeah, so.
Point inside. Coming out.
Okay. So there are two possibilities. Okay. So here's how I like to think of these. All these vectors will be perpendicular, right, to each other. So the force occupies the upward axis, up and down. It's already occupied. Velocity can't be that in that direction. The magnetic field occupies this left and right axis. So the velocity can't be on this left and right. So left and right is gone, up and down is gone, so the whole plane of the board is gone. So I'm left with the option of out or in. Out or in. You take the first, well, try the in, and then try the out. If the in doesn't work, then the out will be the answer. So let's try in. The velocity, let's say it's in, right? If the velocity is in, let me orient my fingers with the velocity, like this. But I want to curl them towards B, but B is this way, so I need to turn this way. Curl my fingers from B to B, that gives me the force upward. So yeah, the velocity is in. Velocity is in, so velocity would be in. That's it, velocity. That's it. Okay, I have an example. Example. Yeah, so let's say we have a current carrying wire. So here is a wire and it carries current. So the wire is going like this. This is the current, and it's 10 amperes. Okay? Current 10 amperes. Now, in what direction is the magnetic field of this wire? At the top and at the bottom. Let's start with the top. In what direction?
Out, or out.
Out, and then at the bottom?
In.
It's in. How do you figure that out? Good. So there is another right hand. You use your right hand to calculate cross products. You also use it to figure out the direction of the magnetic field given a current. So the way to figure out the direction of the magnetic field from the current, orient your thumb with the current, and your fingers would be the direction of the magnetic field. So your fingers will tell you that the magnetic field is curling like this. It goes around. So in here it's coming out, and then it loops around and then goes in. So in here, the magnetic field is out. In here, the magnetic field is in. And obviously I only drew 3, but everywhere here it's in, everywhere above it's out. Okay? Now, suppose you have an electron that is 1 centimeter above the wire. So here is an electron. This is an electron, minus charge. And it's moving in this direction. It's the velocity. Okay? So Q is an electron, so it's negative E, which is minus 1.6 times 10 to the minus 19 coulombs. We're given the current, it's 10 amperes. The distance from here to here is D. I'm going to write it down. D is 1 centimeter, which is 10 to the minus 2 meters. Okay? The velocity of this electron is 10 to the 7 meters per second. And you think you probably know what the question will be. What do you think it's going to be? What is the? We can find the magnetic field, yep, and then ultimately we want the magnetic force. Yeah. Yes.
So current is the movement of positively charged particles,
sorry?
right? Current is.
Yes.
So
Current is positively charged.
Would
object.
the electron be moving to the left then?
Oh, so this is the current. This is an electron by itself.
Oh, okay.
Yeah,
But
so
it was, if it was on it, then it would be, if it was in the wire, it would be to the left.
Yeah. 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 So this is the current. This one is an independent
Okay.
electron just standing out there. So an electron is now moving this way. So first question: in what direction is the force going to be? Magnetic field is up. The velocity is this way. So use your cross product. In what direction is V cross B? Okay. V cross B is down. Yes. So the cross product of V and B is down because again, the magnetic field is this way, V is this way. So curl your fingers from here is V, curl them toward B, so the force is down. I guess this is easier, yeah. So the V is this way, the magnetic field is that way, so I curl my fingers from V to V, so it's down. But the electron is negative, so the force will be up. So we figured the force will be up, meaning the electron will be repelled. It will go up. Okay. Next, how much is it going to be? So we figured the magnitude. So the force, we figured the direction. The force will just be Q times V times B, right? Times the sine of theta. That's the magnitude of the force. But theta is 90 degrees, isn't it? Right? The velocity is this way, the magnetic field is this way. They make 90-degree angle. So this is sine of 90, it's 1. So this is just 1, sine of 90. So we get QVB. And I'm looking for the magnitude. So the charge is 1.6 times 10 to the minus 19. Again, why isn't there a minus sign? Because I figured the direction. I'm just looking for the magnitude. The velocity is 10 to the 7th. Now the magnetic field, who is producing a magnetic field? The current. And remember what the magnetic field due to a current is? U naught. For solenoid it was little n times I, but this is just the current carrying wire.
Mu naught times I. Over 2 pi r.
2 pi r, yes. Yes, mu naught I over 2 pi. So mu naught is 4 pi times 10 to the minus 7. And then times I, the current is 10 amperes, right? Divided by 2 pi times r. R is the distance from the wire to the charge. This is R or D. Over here, they said it's 1 centimeter, 10 to the minus 2, 10 to the minus 2. So we got 2 here, the 2 pi cancels. 10 to the 7th, 10 to the minus 7 cancels. 2 times 1.6 is 3.2 times 10 to the minus 60. U. That's the force. Okay, I'll move on. The next topic is motion of charged particles in a uniform magnetic field. And if we had the lab, we did it in the lab yesterday. I discussed it in the discussion last week also, but we want to derive it in class, maybe derive. I don't know. I was debating whether I should go through all the details. The bottom line, I will tell you what you need to know, the bottom line at the end, but then here is what it is. So let's say you have a region where there is a magnetic field. So here is a magnetic field, right? Magnetic field is here. This N. Now, suppose you have a charged particle, Q. Here's a charge Q. And at this moment, let's say, and by the way, here is my X, Y, Z. At this moment, the particle is moving at certain speed V, right? Certain speed V. And so in what direction would the force on it be if the charge is positive? So plus.
Up.
Okay, would be up, yes. Velocity is this way, the magnetic field is that way. So cross your, go from V to B. So V to B, force will be upward. So a moment later, the force will be this way. So this particle will not go straight, but it will go up. It will go to the right and up. So a little bit later it will be here. But when it's here, it's now moving at another speed. I'm sorry, not another speed, another velocity, but the same speed. Magnetic forces do not do work. I think I said that before. the work done by magnetic field force is always zero. So when the velocity is in this direction now, velocity is in this direction, in what direction is the force? Yeah, so the velocity is this way, the magnetic field is still in, so cross your fingers from V to B, so the force in this case will be this way. So it's always toward, perpendicular to it. And this will constitute uniform circular motion if you continue the path, it will have a uniform circular motion. And it will have a certain radius and so on. So, to understand it, let's write down, we would say, let's say the initial position, the initial position here, our initial is x initial I hat plus y initial j hat. It's on the plane of the board, so no z as well. Okay. Is this okay? I'm just, yeah. So the initial velocity, according to this picture here, let's say initially it's here. You can choose it anywhere, but no necessary. We can choose, we will start here. In what direction is the velocity?
To the right.
To the right. So it's just v I hat, right? Just v I hat. And I just say v because the velocity is good. It doesn't change magnitude. The magnetic field is the magnitude of the magnetic field, but it's into the board, right? So that's what? Minus k hat. Right? Magnetic field is into the board. This is the x, this is the y. So the positive k hat is this way, so the magnetic field is into the board, and it's uniform. It's not changing, so it's just that. Is this okay? So we want to find the velocity at later times, at all times later. So what would it be? Well, the velocity in general, since the force is always on the xy plane, there is no force in the yz direction. So the velocity we expect it to remain in the xy plane. But just for argument's sake, suppose the velocity looks like v is the x component of velocity I hat plus the y component of velocity j hat plus the z component of velocity k hat, even though this one will just not matter. So is this okay so far? So I'm just setting up what I'm going to do. Now let's write down the force. The force is Q V cross with V. Okay, V cross with V. So V Q, and we have to take the cross product. So I hat, J hat, K hat, Vx, Vy, Vz. The magnetic field is does not have an x and a y component, so it's 0, 0, minus. Okay, that's the magnetic field. And to do this, remember you just rewrite the first two columns, right? And then do your cross product. Or use the cross product definition. I'll just use this one because I think it's faster. So you got I hat, J hat, Vx, 0, Vy, 0. And I would go this way. So I get I hat, Vy minus B, and then there is a Q in front. So you get minus Q, B, and then Vy. Oh, I. Is everybody fine with the cross product that I'm doing? All right. So I'm just doing a cross product. Okay. So that's the force. And then we have to do this with the other side. So this one. And by the way, these were 0, right? J hat Vz times 0. This one K hat Vx times 0. So now this side you have to put a minus sign. So you put J hat Vx times negative V, but there is a minus sign because we're going this way. So V plus QBVX, QBVX, J hat. And then these will just give you a 0. So that's the force. Now Newton's second law says F equal to ma, right? Force equals to the mass times acceleration. It still applies. So F equal to ma, the acceleration is dv dt, right? So F equals to the mass times the acceleration. So the acceleration is dv dt for the acceleration. So we have this. Let's write it down. dv dt. So let me write down the force first. So on the left side I have minus q b vy I hat plus q b vx j hat equals to the mass times acceleration. M times dv dt. But dv dt is, take the derivative of this, you get m times dv dx I hat, or dvx dt I hat, and then the derivative of this with respect to time j hat, so m dv y dt j hat, and then the z component plus m dv z dt j hat, k hat. Okay, so now notice you can equate the I hats together, the j hats together, right? Right, two vectors are equal if and only if they point in the same direction, they have the same magnitude. So the I hats together, the j hats together, but the k hat does not have a k hat on this side. So what's the acceleration in the k hat direction? Zero, no acceleration in the k hat direction, because the force is on the xy plane, which makes sense, right? F equal to ma. If you don't have an acceleration in that direction, there is no. If you don't have a force, there is no acceleration. So good. So here's what this one gives me. I'm going to equate the I hats together, so I got this. The x component dvx dt will equal to this minus q b over m dy. Okay. And then for this, I'm going to equate these two. dvy dt is equal to qb over m dx.
Professor, can
Yeah.
you explain how you got those two equations again?
Which equation? This
Those-
one?
Yeah.
Yeah.
Why can we set them equal?
Yeah, so if you have two vectors, then you can match their components, right? So this I hat component matched with this I hat component. So this is m dvx dt, and this one says minus qb vy, right? That's the I hat. So when you set them equal and divide by the mass, you end up with this one. Just make sure I have it. Vy, okay. For some reason, my notes, I have this one as positive and this one as negative. Did I make a mistake somewhere? Or it's okay? It's fine, right? Maybe my notes are wrong. All right, let's go on. Anybody suspects we made a sign mistake? I think the cross product looks reasonable to me.
I mean, it's accelerating upward in the y direction, right?
Yes.
So it should be positive, I guess, unless it.
Well, this is the acceleration in the x direction.
Oh, okay.
This is the acceleration in the y direction.
Okay.
So I guess it's fine. Yeah. Yeah. All right. So these are the two equations we're going to work with. Yeah. I'll go.
Wait, sorry, could you say one more time why you're multiplying by the velocity in the y direction, the velocity in the x direction? What's the
Here?
Yeah.
Oh, so do you agree with this equation?
Mm-hmm.
Okay, so I said this. You see the I hat here
Oh,
and the I hat here, and I matched them together. So this part of this I hat matches with this one.
Okay.
There was a hat.
Oh, so then DEVZ DT is just zero.
That one's zero. Yeah, this one, the left side doesn't have a K hat, so it's zero. Okay. So notice, and okay, which is a good point. You're saying here you got Vx and this one is Vy, right? And we need to decouple those equations. You can't have the x depending on the y. So the trick is this. Take the derivative with respect to time again with both sides. That's what we're going to do. So here's what, and I'm going to try to do it on here just to save space. Okay. Yeah. So let's take the derivative of this with respect to time, both sides. When you take derivative here with respect to time, you get the second derivative, right? On the left-hand side, you get the second derivative. So you get the second derivative of Vx dt squared is equal to negative qb over m and then dvy dt, right? If the derivative with respect to time on both sides. Why do I do that? Well, look at this. What does this equation say dvy dt is? Huh? It says it's qb over m vx, right? Well, replace dvy dt by qb over m vx. What do you get? Okay. So I need to speed it up a little bit. Okay, and then yeah. So I will replace this dvy dt by this. This is dvy dt. It's equal to qb over m dx. So when you do that, you will have qb over m multiplied together. That's minus qb over m to the second power, and then you get vx. And I'm going to do the same thing here. I'm going to take derivative of this with respect to time. So you get the second derivative of dy, second derivative of t, right? Taking the second derivative, and then derivative of this with respect to t. So you get qb over m dvx dt. So, but dvx dt is minus qb over m dy. So when you replace it, you will get minus qb over m squared dy. So we're going to make the notation a little nicer. So we have this. The second derivative of vx with respect to time. Second derivative of vx with respect to time is equal to this minus. I'm going to name this just omega. So omega squared vx. And this one here, very similar. So we're going to get d squared vy dt is equal to minus omega squared dy. And I'm defining omega to be q e over m. That's omega. Just defining an omega like that. Okay. Why am I defining it that way? Well, it will be a circle and it will have a certain frequency. And so that's why I define it. So now we're going to look at this equation here and solve. So you have the second derivative of a certain quantity is equal to that quantity back with a minus sign. So what's the answer to that? Which function? When you take its the second derivative, you get back the same function. How many? E to the power x will give you just e to the power x again with a power. No, you will get the negative again. Negative twice because you take the derivative twice, you get it back.
You get negative e to the negative?
No, you get it same thing. You can take the derivative twice and see. So e to the I, if you have the used imaginary numbers, e to the I t or something, I omega t, then yeah. That's what you, because I times I is, right, I is the square root of minus one. We don't have to go there, even though it's related. Yeah,
It's sine.
sine or cosine, yes. Yes, it is a sine or a cosine. So looking at these equations, we're going to use we're going to say, so the general solution to the top equation, dx, will have the following form. It's some thing called a, some constant. I'm going to figure what that constant is, times the cosine of omega t plus p1. This is just a phase shift, we need to figure it out. Okay? So that's the general solution to this, to that equation. Yeah,
Are both of the equations differential equations?
I'm sorry?
Are the two equations like
Yes,
differential equations?
yes, I didn't use the word, yes, they are differential equations, yes. Yeah, there are two differential equations, second order. Yeah. We encountered this, we encountered it all in physics 130 when we did mechanics, simple harmonic motion. So that's the solution to that one. Let's look at the solution of the Vy, very similar. Vy, it is some second thing, cosine of omega t plus some t2. Okay. Now we're going to use the initial conditions. So at t equal to 0, what was Vx?
Just V on V.
Yeah, it was just v. I mean, the x component is just v. Right? The y component is what?
Zero.
Yeah, 0. Right? It just has an x component. It's moving just to the right. So the x component initially is just v. And plug in t equal to 0, you get a cosine of t1. Alright? Now, how much is phi? Well, I know that the amplitude has to equal to v. How do I know that? Well, the velocity has a magnitude v because it was moving only in the x direction and it's v, so the magnitude is just v. Right? It doesn't have any y component, so the magnitude is v. So the x component initially at t equal to 0 cannot be less than v. So if phi is not 0, right? If phi is not 0, then in that case a would not be equal to v. So phi, or phi1 has to be 0. This phi has to be 0. Okay, so that's the argument. Phi1 has to be what? So imagine I say phi1 is 30 degrees. What's cosine of 30? Square root of 3 over 2. Square root of 3 over 2 is less than 1. So that says a times something less than 1 is equal to v. So a ends up greater than v. But the velocity, the maximum velocity is just v. Right? The velocity that the speed we're working with is v of this particle. Okay? So it's always v. And I would emphasize later that magnetic forces do not do work. They do not do work, meaning they do not change the speed. Okay? They don't change the kinetic energy of the object. Okay, so phi, that's the argument. Phi is 0, and therefore a is equal to v, and so